In this video, we're going to dive into the world of art, perception, and machine learning. Specifically, we'll talk about how researchers in the Grappa project are trying to figure out what makes certain images more aesthetically pleasing to us. My colleagues and I work on the Grappa project, where our goal is to connect aesthetic preferences for paintings and photographs, how much people like an image and why, to broader principles of perception. These are the techniques our brains use to interpret what we see. Our team is a mix of perception scientists, machine learning engineers, and statisticians, all working together to crack the code of what makes images appealing. One of the components we study is symmetry. Symmetry is all around us, in nature, architecture, and in art. Our brains are naturally wired to find symmetry pleasing because it helps us make sense of the world quickly. Think about how we recognize faces or appreciate the balanced design of a building. By studying symmetry, we can better understand why people find some images more beautiful than others. The way we tackle this problem involves a few key steps. First, we collect new data through online studies and psychological experiments. Second, we analyze this data using advanced computational methods, like machine learning, to find patterns. Finally, we use these patterns to build models that predict aesthetic preferences and help us understand what features really matter in making images aesthetically pleasing. One of our projects aimed to develop a model that could create heat maps, highlighting symmetry axes in artworks and real-world images. Heat maps are just images where colors represent different values, kind of like a weather map, where red means hot and blue means cold. To make this work, we ran an online study with over 900 participants. They looked at images and marked as many symmetry regions as they could spot. The study gave us a dataset of 400 images with over 35,000 symmetry markings. But there was a problem. Multiple people often marked the same areas, so the raw data was messy and full of repetition. That's where clustering comes in. Clustering is a technique that helps us group similar data points together. Think of it like sorting a bunch of puzzle pieces into groups based on color and shape before putting the whole puzzle together. We use clustering to group symmetry markings based on their size, position, and rotation. The algorithm reduced the data from thousands of points to a handful of points per image. That represents areas where a lot of people indicated symmetries. Consider this example. One image has two cluster areas, one with 40 people indicating it as symmetric and one with 20. By looking at the number of data points each cluster has, we can have an idea of how symmetric each specific region of the image is. But even after cleaning the data, we faced another big challenge. Our dataset was still too small for training deep learning models. Machine learning algorithms need thousands, sometimes millions of examples to learn effectively. But collecting human-labeled data at this scale is incredibly expensive and time-consuming. Imagine the amount of time it would take to get thousands of people to mark symmetry in millions of images. To solve this, we turn into synthetic data. Synthetic data, it's artificially created instead of collected from real-world resources. In our case, generating synthetic symmetric images was pretty straightforward. We took simple shapes, copied and mirrored them to create perfect symmetry, and added background noise to make things more complex. This allowed us to generate thousands of images where we knew exactly where the symmetry was, which is very useful for training AI models. Let's understand better the training process. It's basically two steps: pre-training and fine-tuning. Pre-training is a technique in which we first train a model with a large dataset for a general task. We use our synthetic data to pre-train a UNet, a type of convolutional neural network, to recognize symmetry in simple shapes. Then we fine-tuned it, train it again on a smaller and more specific dataset, using our human-labeled dataset. This step was key. Because while the pre-trained model could spot basic symmetry, fine-tuning it really helped it better adapt and mimic human perception of symmetry. Here's an example of the model predicting symmetry after being trained only on synthetic data and after fine-tuning it with real data. Red areas in the image represent predicted symmetry axes. You can clearly see how much better the model performs after incorporating human label data, refining its understanding of symmetry and making its predictions more aligned with human perception. Training artificial intelligence models to mimic human perception isn't easy. While machine learning models are inspired by the human brain, they don't think like we do. One of the hardest parts is the lack of large, high-quality datasets. That's why creative solutions like synthetic data are so powerful. They help fill in the gaps in areas where collecting more data would be too difficult. If we want our models to understand aesthetics as a whole, we first need to teach computers what symmetry is. By combining human-labeled data and synthetic images, we can build a system that understands symmetry in a way that's closer to how humans see it.